So when you burn something, it gives off two things. It gives off heat, which warms the earth immediately, and it gives off CO2, which is a greenhouse gas that insulates the earth by inhibiting its ability to emit into space in the infrared. People talk a lot about how this is causing the greenhouse effect, heating the earth, but we don't talk about how do these relate. And someone once asked me, what heats the earth more? The direct heating from the heat of combustion or the greenhouse effect? And they're very different. We get this heat immediately, and this warms the earth consistently over a long period of time. So the real question is, how much time does it take for this CO2 to warm the earth as much as this amount of heat given off immediately? And so we can take the example of coal, which has a carbon intensity of 25 grams of carbon, or 90 grams of CO2, per megajoule of heat given off. So if we burn enough to give us 1 megajoule of immediate heat, we get 25 grams of carbon. So how long does it take this 25 grams of carbon to warm the earth an equivalent of 1 megajoule? And so we look at how does this heat the earth? Well, we have what we call radiative forcing of 1.4 watts per meter squared over the whole earth. This is the present radiative forcing from all the anthropogenic greenhouse gases that have ever been emitted. And when we say that, we mean over the past 100 or so years. And so when we look at these emissions, some people say it's exponential, but we can estimate it as a linear function that begins around 1930 up until now, 2015. And the part that we lose here, we gain here, and it's about the same. It's about a triangle. And right now our emissions are about 10 gigatons of carbon per year. And so this is the year 85 years. And we can estimate the area of this triangle, 1/2 base times height, as the total amount of emissions of all time. So the area of this triangle years cancel, and I get 425 gigatons. Okay, so a gigaton is 10 to the 9th, and a ton is 10 to the 3rd kilograms, or 10 to the 6th grams. This is 10 to the 15th, 16, 17, 10 to the 17th grams. So now we can find the radiative forcing due to just this 25 grams by assuming a linearization that this little bit of increase is going to increase the radiative forcing by the same percentage. So the radiative forcing from this 1 megajoule of heat given off is equal to 1.4 watts per meter squared times 25 grams divided by 4.25. Now this is going to be a small amount. This will be on the order of 10 to the minus 15 watts per meter squared. However, this is over the entire surface of the earth, so if we want to find the power, the equivalent power that this radiative forcing is providing to the earth's surface, we need to multiply by the area. So this is the radiative forcing term, and we have 4 pi r squared, where r is the radius of the earth. That's 6,400 kilometers, or 6.4 times 10 to the 6th meters. We can solve this a couple ways. If we multiply this by 100 and divide this by 100, we can see this is 17. 4 pi is 12. So this turns out to be about 10 to the minus 15 watts per meter squared. And then this comes out to be, well, 6 squared is 36, so 6.4 is about 40. This comes out to be 40 times 10 to the 12th meters squared. And these cancel. 10 to the minus 15. This gives 10 to the minus 3, 2, or about for 40 milliwatts, or 0.04 joules every second. And we want to know how long does it take this small amount of power to provide us with a millijoule. We know that power is equal to energy divided by time, and so time is equal to energy divided by power, which is 10 to the 6 joules divided by 4 times 10 to the minus 2 joules per second. Joules cancel, and I end up with 0.25 times 10 to the 8th seconds, or 2.5 times 10 to the 7th seconds. What we remember is a year is equal to about pi times 10 to the 7th seconds. And so this is 2.5 over 3.14, and so we're talking about 9 months. So when you burn some coal, you also have an incubation period of about 9 months for that heat given off to be equal to the amount of warming you get from the greenhouse effect. And so the next 9 months, you'll get it again. And the next 9 months, you'll get it again. And so this is why this is a much greater warming factor, because over time, it will continue to warm the Earth. Now you take a look at what about natural gas, which provides only 15 grams of carbon per megajoule. And so its effect is going to be smaller by 10 parts in 25, and that's 2 parts in 5, which is 40%. So it's going to take 40% longer for it to provide that same amount of heating. So 40% of 9 months is about 4 months. It would take on the order of 12, 13 months for its 15 grams to heat the Earth as much as the megajoule that it's emitted. And petroleum is halfway in between. So if you burn some coal, it will take about 9 months for the greenhouse gases to heat the Earth as much as the immediate combustion heated the Earth from the burning. If you burn natural gas, it'll take about 13, 14 months. If you burn some petroleum, it will take 10 months, 11 months. The key is the combustion energy you get right away, where the greenhouse effect continues every year, you get that much more. Is this an exact calculation? Absolutely not. For one, we did a linearization saying that this incremental amount of carbon would heat the Earth proportionally with as much as you gave it. That's a bit of an overstatement, because as we continue to add carbon, the effect of each little bit is somewhat less than that before. So this is somewhat of an underestimate. Likely it may be slightly more than 9 months, slightly more than 13 months, and slightly more than 10 or 11 months for petroleum.